This is Rebecca Evans from the Space Weather Center at NASA Goddard Space Flight Center. This video reports on the activities associated with active region 1429. On March 2, 2012, active region 1429 rotated onto the Earth-facing solar disk. For the last 25 days, it has been in continual action. The timing of major eruptions, however, has been somewhat erratic. During the period of March 2nd to 15th, it rotated across the solar disk and fired off more than 50 flares. Flares are classified by their intensity. There were 32 C-class, or common flares, 15 M-class, or moderate flares, and 3 X-class, or extreme flares. All 3 X-class flares were accompanied by very fast and wide coronal mass ejections, or CMEs. See the link below for a summary video of the 2 X-class flares and CMEs that occurred on March 7th. The M-class flares from this active region that occurred on March 4th, 9th, 10th, and 13th were dramatic as well. Each produced a fast and wide CME with speeds exceeding 2.5 million miles per hour. That's 2.5 times the average speed of CMEs, which typically clock in at around 1 million miles per hour. The evolution of the active region and its major flares and CMEs can be seen here on NASA's Integrated Space Weather Analysis System, or iSWA. The images come from NASA's Solar Dynamics Observatory, also called SDO. Here are the major flares seen by SDO's Extreme Ultraviolet Variability Experiment, or EVE. The flares are so strong that they saturate the instrument, as can be seen by the bright white circle in the image. And now we see the same flares viewed with the SDO's Atmospheric Imaging Assembly, or AIA. These images show light at the 131 angstrom wavelength. This wavelength shows plasma at temperatures greater than 10 million degrees, which is particularly good for viewing flares. On March 16th, the active region finally rotated off the Earth-facing solar disk. When features on the Sun move behind the Earth-facing solar disk, we can still view them with the imagers on NASA's Solar Terrestrial Relations Observatory, or STEREO. There are 2 STEREO spacecraft in Earth's orbit, one drifting ahead of the Earth and one drifting behind. They are called STEREO A for ahead and B for behind. The action continued with 4 events on the backside of the Sun. Here we show images from STEREO A and STEREO B Extreme Ultraviolet Imagers, or EUVI. These images show light at 195 angstroms. This wavelength shows plasma with a temperature of 1.4 million degrees. Of the 4 backsided events, the first 2 were viewed by STEREO A and the second 2 by STEREO B. If you look carefully, you can see the material from the CMEs and associated waves. On March 18th, around 4 a.m. Eastern Time, the region erupted with a sizable CME with a blistering speed of over 3.2 million miles per hour. Then, on March 21st, around 4 a.m. Eastern Time, it shot off yet another CME, this time with a speed of over 3.5 million miles per hour. Unbelievably, around 8 p.m. on March 23rd, an even faster CME erupted with a speed of about 3.6 million miles per hour, with its flank impacting STEREO B. Once again, on March 26th, around 7 p.m. Eastern Time, the same region gave off another CME with a speed of 3.2 million miles per hour. Consequently, the energetic proton radiation level at STEREO A was elevated almost immediately following the onset of the first 3 backside events, and the proton radiation level at STEREO B started elevating with the 3rd and the 4th events. At the NASA Space Weather Center, we use a large-scale heliospheric model called INLIL to estimate the path of CMEs as they travel through the solar system. Though the CME propagation direction is not linearly correlated with the CME's initial location, the location of the active region, its temporal evolution with the active region from more east-oriented to more west-oriented is evident from our predictive model results. Over the last 3 weeks, our forecasts of the arrival time at different objects in the solar system were generally close to the actual observations. At Earth, the strongest space weather impacts were due to the 2 X-class flares on March 7th. The Geomagnetic Activity Level Index, KP, a scale from 0 to 9, reached 7 between 1 and 7 a.m. Eastern Time on March 9th. The KP index was also enhanced on March 7th, 12th, and 15th. In all 3 cases, the enhanced activity can be attributed to the interaction of a CME with the Earth's environment, or magnetosphere. These CMEs were associated with the X1.1 class flare on March 4th, the M8.4 class flare on March 10th, and the M7.9 class flare on March 13th, respectively. The flurry of activity has also boosted Earth's radiation belt energetic electron fluxes since March 10th. At the same time, the energetic proton radiation level for particles with energies greater than 10 mega-electron volts was the highest since October 2003. 2 major episodes of energetic proton radiation enhancement in the near-Earth space were due to the solar activities on March 7th and 13th. The energetic proton radiation caused by a flare-CME pair tends to be broad in space. For active region 1429, the peak impact was at stereo B first, then it rotated to Earth, and finally reached stereo A. Active region 1429 has certainly kept people involved in space weather operations busy, in addition to stirring up a media sensation. The active region's long duration and seemingly dangerous appearance did not translate into severe space weather impacts that many had feared. Nevertheless, it has dominated space weather conditions throughout the solar system for more than 3 weeks, a little shy of 1 solar rotation, or about 27 days. The long-lasting nature of its activities may give us a new glimpse into the inner workings of solar activities that are the major and ultimate source of space weather. Hopefully, the wealth of data collected from NASA and other missions during this period can help us unlock many hidden secrets of space weather.
All of the data in this video is accessible from our Integrated Space Weather Analysis System, located at iSWA.gsfc.nasa.gov. Thank you for watching.